All right, welcome back. This is unit 3.3, and it's the beginning of continuous random variables. So let's quickly go ahead and review. In the previous section, we went ahead and described discrete random variables. And this is when we went ahead and counted. So the random variable x was equal to the number that was found by counting. And some of these outcomes were, for example, the number of successes or the number of individuals that arrive at a certain place. And that was discrete. So let's just quickly remember that we described the distribution. And the distribution of a discrete random variable was represented. We started by representing the distribution of the discrete random variable with a table. And so we went ahead and said, well, if I can describe the outcomes, if my random variable can take on value little x, and if I can also go ahead and describe the probability of that outcome, and let's go ahead and pretend that I went ahead and did this for value number 1, value number 2, and so on, then this is the distribution of the random variable x. And we also went ahead and described that distribution graphically. So here on the x-axis, we have the outcome. So this would be little x. So these are the outcomes. And we can go ahead and say that if I want to observe the random variable have a value of 0, then there is a corresponding probability. So on the y-axis, we would have the probability that my random variable x takes on that specific value. And we can observe just visually, graphically, that this value here, that's 1, 2, 3, 4, 5, 6, that the value of 6 has the highest probability. So the probability that x equals 6 is very high. All right, and so in this section, we're going to go ahead and continue with these ideas, but we're going to change it. So remember that we started by saying that random variable could be either discrete or continuous. We've already covered discrete random variables in the previous sections. Continuous random variables are going to be what we look at now. So let's start by looking at the difference between these random variables. If you have a continuous quantitative value, so let's go ahead and say that we have a quantitative variable, but continuous. And remember that continuous means that you can get any value within a range. And usually we know that we're dealing with a continuous random variable because it is a variable that we have to measure. So if we measure with some tool, then we're probably dealing with a quantitative variable. So one quick example here could be, for example, the amount of coffee in a certain cup. That'll be in ounces or milliliters. Or I can even talk about the height of the cup that we get that coffee in. And again, that needs to be measured. So there's a tool that I got to use. Here, let's go ahead and pretend that we're dealing with the temperature. So I'm going to go ahead and let the random variable x be the exact temperature to degree Fahrenheit for this cup of coffee. And note the following. Potential values for x could be 90.0 degrees Fahrenheit. It could also be 90.01, 90.001, 90.0001, and I hope that you more or less get the idea here. It doesn't make sense for us to actually use tables because of this problem. There's no way that you're going to be able to enumerate all of the different temperature values in a nice, concise way. So because of that, because there's this whole range of values, we need to recognize that the values for x now occur within a certain range. And so here we have the range from 5 to 8, including 5 and 8. But it could be that the random variable of interest could, for example, not be bounded. And so we now have a big difference from the previous section, which is we cannot make these tables anymore. to describe our random variable. Now, all hope is not lost because if you remember, not only do we have a table, so if we can't do the table anymore, that's fine. We can always go ahead and use a graph. And so that's what we're going to go ahead and do. And that's what you want to really get comfortable with in this section. So let's go ahead and just state that we're now going to go ahead and describe the continuous random variables by something called a probability density function, or PDF. And the reason for that is that this more or less describes how likely an outcome is visually. And you shouldn't be surprised by this because we've seen that if you have a variable that is continuous, we want to visualize this with histograms. And the more data you have, the smoother the histogram will be if you make the class widths smaller and smaller and smaller. And you can go ahead and more or less get an idea that, hey, this is your data. This is the distribution of the data, right? We get an idea of the potential values as well as how likely those values are. And the more bins that we use, the smoother this layout of my data becomes. And you can imagine that if we just collect more and more data, that eventually it doesn't really make sense for us to use all those steps. So we're going to go ahead and get a smooth graph. And so this smooth graph or smooth curve is what's called the PDF. For us, we're going to just say when I ask you, can you describe the distribution? I'm probably going to be asking you to draw. So for us, we want to just think of the distribution as being this graphic that is more or less going to describe the behavior for our histograms. So don't worry too much about the terminology of PDF. Just know that now we're going to be using graphs to describe the random variable rather than tables in the same pattern that we use graphs to describe discrete random variables here. But now instead of just solid heights like this, we're going to have a curve. All right. So let's just develop this idea further. So the main thing to know is that for continuous random variables, so if random variable x is some continuous random variable, then it's going to have these properties, which is if you draw the PDF, so if you draw its distribution, so from here on out, let's just go ahead and attach PDF. Probability density function is going to be synonymous with distribution. All right, now when you draw these, you want to make sure that the entire curve lies above the x-axis. And the reason for that is that we're trying to describe how likely something is to occur. So it doesn't quite make sense for us to describe likelihood to be negative. So that's something that we've already seen. We had that before when we said the probability has to be valid. So the probability that a random variable x takes on a specific value has to be greater than or equal to 0. The area under the entire curve has to be 1. Because that you're basically saying you're going to get some value, and the probability of that is 1. So we had that before in the previous section when the sum of all the probabilities over all potential values had to be 1. And so that's the equivalent result we have here. Now, what I want to emphasize is the following. The probabilities are now areas. Trying to see if I listed that here. So probability that A is less than X is less than B is the probability of random variable typo X being between A and B. Okay, so that makes sense. Okay, so I don't see it, but here we go. That's good enough. So this basically says that if now I'm trying to find the probability that my random variable takes on the value between x1 and x2, that I can go ahead and then just simply ask, well, what is the area under this curve? And notice that that's very similar to what we had prior, because when you made these distributions here in the previous set of notes, for example, when you're finding the probability here that the random variable x is 1, we can see how StatCrunch highlighted that bar at x equals 1. And you can imagine that if we had another bar here at 2, and then you're finding the probability that x is less than or equal to 2, then it would highlight this bar at 2 and this bar at 1. And notice there is no highlighting between 1 and 2 because this was discrete. For continuous random variables, we want to go ahead and say, well, we'll be happy with either of the values, any value that's between x1 and x2. And so that's part of the reason why we're finding these areas here. So this probability that we find, for example, if my distribution is kind of flat like this, or whether it's bell shape, and I have the value x1 and x2, the region in red is the probability for that. So that's the main difference. Probabilities are now areas. All right, and so please make sure that you also go ahead and read these bullet points here about facts for this probability function. That's more or less the introduction here. Let's go ahead and do a quick example before we move on. So this is the beginning of the first kind of random variable that we're going to look at, which is the uniform random variable. And remember that we are essentially measuring some continuous variable. And for example, we can go ahead and say that that variable is equally likely to occur between two given values. Those values are called A and B, and those are known as parameters. Because as soon as you know what that value A is and what that value B is, you have a complete description of the distribution of the random variable. So the way that we write that is we write that X tilde U for uniform, and then we write the parameters A and B. And what we're basically going to say is that this box represents the total area, and the box would need to have an area of 1. And so remember that the area of a box is just base times height. And the base we know, it's B minus A. The height, if we don't know, but the area has to be 1. So therefore, the height has to be equal to 1 over B minus A. You don't have to memorize this. This is something that's going to be given if needed. But yeah, this function here is your PDF. Or remember your distribution. And what I want to emphasize is that on this x-axis, your distribution is 0 if x is bigger than b, and 0 if x is less than a. Because we just said that my random variable, whatever I'm tracking, has to occur between a and b. So it cannot possibly occur to the left of a or to the right of b. So if you were to make a histogram, there would be no height to the right of B and no height to the left of A. But there will be more or less heights that are around the same height between A and B. So you could get something like this. So just think about that the distribution would essentially describe how a sample would look like if you create a histogram. All right, I think I'll end here, and then we'll complete this example in a separate video. Thank you for joining me. We'll take a look at this in the next section.